Good morning, students, and welcome to the another session of Structural Analysis 2. I advise those are joining, please enter your details in the chat box, and then within a couple of minutes, we can commence the session. So join fast, and you can spread a word across the group that we are already on. So stay tuned, and within two minutes, we'll start. And meanwhile, you can collect your writing tools with you so that in parallel you can do your exercise with me. I can spot that students are joining gradually, but ask them to join fast so that we don't waste our time. And also those who have joined on time, it will be justifiable to them also. So meanwhile, friends, you recently have appeared in your exam, and with your recent experience, uh, before we progress, I would like to have a word with you regarding your feedback, regarding your experience of appearing in the examination. So it would be good that someone, few students from you become volunteers, and if you can discuss your overall experience of appearing in the examination so that I also get a feedback that whether we are doing fine or we are going in a right direction or not. And similarly, do we need to change the style of working, style of delivery? In case if it is required, then we can definitely think over it. So who would like to discuss with me? Raise your hand so that I can unmute him or her. The purpose of this discussion is to get your inputs and feedbacks on the experience, overall experience appearing in the examination. Recently, your mid-semester exam was there, and most of you have appeared over there. Since it was the first offline exam, I suppose, in which you appeared as far as the numerical subjects are concerned. So I understand that you may have feel some challenges regarding transforming the digital knowledge into the actual knowledge in the answer sheets, right? So, friends, who would like to discuss with me, or should I name individually? And accordingly, you can respond to me because your inputs are necessary for me. So, let me go to Darsha first. Darsha, are you there? I have unmuted you already. Try it now.
Yes, sir. I found lengthy paper.
So the question paper was little lengthy. That is what your feedback, right? So why you felt
Yes,
lengthy? Like what? According to you, what may be the reason for that? What may be the reason, like why you felt it lengthy? Any particular reason? So if I
Sir, my
discuss, yes,
and practice.
practice. Okay, you were missing or you were running out of practice. You probably could not do practice enough, right?
Sir, I do, but I'm not able to complete in within time.
Mhm. Okay, so that may be one of the reasons why you felt the paper lengthy. So that is one feedback. That is fine. But Darsha, if we discuss about the level of the paper, like below average, average, or above average, or let us say very easy, easy, or medium, or hard, in that parameters, can you share it with me? Like, what did you feel about level of the paper, academic level of the paper?
Sir, easy.
Easy. Okay. So according to you, the paper was not tough, let's say, and nothing was there which you could not understand or you could not respond to, right? So, okay, thank you, Darsha. And let me go to someone else. You can mute yourself now. Yes. Who would like to share another feedback? You can be an individual, raise your hand so that I can also unmute yourself so that I can get some constructive feedbacks. Anyone? Let me go to some students. Let's say Eric. Uh, Eric, you can unmute yourself. Are you there?
Yes, sir.
Okay, so tell me, Eric, what was your experience appearing in the mid-sem exam?
It was good. The only challenge was managing time.
Yes, so time
Yes,
management was a primary concern. That's right. That's right.
yes,
But
sir.
yeah,
And then it also involved calculation from the beginning to the last. So for us, we are not. I think the only problem was about time because from number one to the last was just calculations and writings. Yeah. So that's why we found it a little bit tricky.
okay, all right, all right. But
Yes.
okay, but regarding the level of the question paper, like it was medium, like was not tough. That's what you found, right?
No, 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 not at all. It was not tough. It was just okay.
Okay, very good, very good.
Yes, sir.
So thank you, Eric, for sharing your feedbacks again. And
Oh,
yeah, okay, thank you. So this is how we also learn, like being a faculty, we also learn from the students, like what you feel about when we ask questions to you. Largely they are similar, largely they are exactly the way in which we have discussed in the uh, classes. Generally, we have offline classes, and that is where we are also there in your classroom. So what happens is we make you work in the notes, and that is how you also get to know how to solve the question, particularly in a given time limits. So we have received two or I mean couple of feedbacks where the general notion which I have developed from your side was that paper was little lengthy, like in terms of you didn't have enough practice probably, where if you could have practice on your own, I'm sure that this is not the common story, but for most of the students, those who knew and those who are confident, those who were confident that they can solve the numerical. But the thing was, since last many lectures we have been doing it online, and recently the severity of the COVID has slowly getting released, and we are slowly coming into the original mode of learning, that is offline learning. So it will take some time from now. But one thing I would like to discuss with all the students, those who have joined here, that since long we have been appearing in the online sessions, but at the same time, uh, I have always advised all of you, or given a hint or tips always to you, that please practice. If you practice at least one numerical of your particular method that you have learned today in the class of SA1, SA2, by any of the faculties, whether it is me or any other faculty. So if you do a little practice, like spare half an hour on a solution, how to calculate, how to do the calculations, I think you could have performed better with the time limits also. Because as far as the concepts are concerned, I don't think that we have any serious issue regarding the concept clarity, or how to use the principles, where to use the principle, appropriateness, stepwise procedure. Nothing, I think, should have been a challenge to most of you, right? So that is what I take it from the general feedback from you, that you felt it lengthy. That is fine, but that was not because of the nature of the questions. However, we also took care that students must not get troubled with the data. So we kept it as far as possible straightforward. But even though I would say that still people have struggled as far as the theory part was concerned. Like, even most of you didn't wrote the definitions correctly. It was asked that what is the second energy principle. That was a very simple question, but even you could not answer it, since it was not more than a single sentence expression. Like, you just need to require to say that the stored energy is always minimum. That's it. So that was the second principle, and even though we could not perform well in that part, so I would like to advise all of you that whenever you get to know to the another method or new principle, before applying it, please understand it clearly, completely, right? So that you can develop your insights in a numerical solution also. So if you are clear in basics, if you are clear on how to do, what to do, then it becomes very easy for us to apply those things in the numerical exercises. That's what I feel, right? So with this notion, I would go ahead with the content, that is one pending topic in your syllabus, that is regarding the energy principle again. However, it has no direct relation with the energy principle, but it is a very popular method of solution of the structural quantities. Now, it comes with a variety, it comes with the speciality that it is applicable to the both, like determinate as well as indeterminate structure, and that is known as the unit load method, right? So I'm going to start that, commence that. So I wish that every one of you should focus here. And first of all, let me show you what is actually, and then we'll go to the numerical solution. Most of the things are well known to you, like the basic or principal relationship between the sum of the equational data. So you don't need to worry about on that part, but again, let me demonstrate it. So first of all, let me explain with a very simple numerical. I will also compare this method with your earlier methods also, so that you get to know what are the details, what are the differences, and what are the similarities between the two methods together. Now, suppose I have a cantilever like this, okay, and I have a load of 10 Newton here, And suppose this is A and B, right? Now this is a very simple structure. It is determinate also. But suppose I want to find, it becomes very easy for us to utilize the any of the previously learned method like moment area method, like Macaulay's method and other similar methods to find out the values of the deflections and rotations at the specific point over here in such a very simple case. But again, there is a method called unit load method, right? So, or virtual load method, where suppose I am interested to find, let's say, deflection at point C. And let's say this is your 2 meter length of the beam, and that's your 3 meter length beam. Okay. So now I'm going to demonstrate how to utilize this unique load method. What are the specialities? So let me first of all show you what are the significant parameter of this method. So in this method, the only thing is you have to apply unit load, unit quantity. Suppose if you are concerned with the deflection, so in case of deflection, in case of deflection, or you need to apply unit rotation, unit moment, let us say, in case of rotation. So in case of rotation, you need to apply unit moment, and in case of the deflection, vertical deflection, you need to apply unit load to the original structure and develop general equation, general moment equation, and integrate it. Now how to do it? Like, you have to apply all things separately now in this unit load method. So let me first of all write down this name of method is unit load method. So today's focus is on unit load method. So far we have completed applications and understanding on energy principle 1 and 2 for variety of the structures, including trusses, frames, beams, determinate, indeterminate structures, all right. So now this unit load method is a versatile method again, which you can apply on any type of structure, determinate, indeterminate both, and to find out deflections, rotations, reactions, and thereby you can later on, you can find the other internal forces also in a structure, right? So now let me show you how to apply this unit load method. So for that, suppose in this case, let me go back to this question. This is our example today. So here I want to find deflection, vertical deflection, not of point B, but point C due to this external load, right? So what should I do? First of all, I just need to consider two conditions. In first condition, I will be considering the load, that is externally applied load at the original state, in the original condition. Let's say this is C, this is A, this is 2 meter, this is 3 meter, okay? And plus, since I'm interested in delta C, let me write here delta C. So when you are concerned with deflection, you need to apply unit load, as you can read in this statement. So in this case, I will be applying a unit load only. Please understand, I'm applying only unit load at the desired point where exactly I am interested to find the deflection. So here I'm interested to find deflection at point C. At that time, I will not be considering any of the externally applied force. So here in original structure, you can see that we have 10 Newton originally applied, but here I will only consider a unique load which is applied at the desired point in which we are interested to find the deflection. Now, having said this, we will call general equation due to only the external load, that is capital M, and we will denote the general moment equation due to the unit force in the structure by small m. So what ultimately you are going to do is you have to arrange these terms in terms of, let us say delta C is equal to 1 upon EI 0 to L integration, where capital M into small m dx. So this is what is the general expression for your calculation of delta C. Now it is needless to add to you that tell you that 0 to L represents all the segments. So this is generalized equation which you need to first of all develop segment wise, and segment wise you need to calculate, you need to develop the moment equation and unit moment equation also, unit force equation also, right? Now how to do and what to proceed, let me demonstrate it. So this was your first step where you need to apply unit load at the desired level. Now second step is again very easy for you to understand because you have passed through this condition. We will divide this entire beam into two components. First is B to C and then C to A. So let me write them here as a component where B is the origin, right? And I will write B to C as the segment. I will also write its length 0 to 3 meter in the question as it is given in the question itself. And now it's a right time to develop first equation due to externally applied forces. So I'm writing generalized equation by traveling from origin to the beam at an x distance due to the external force. Please understand. So capital M is nothing but the generalized moment equation developed in the particular segment due to external load only, exclusively. So there is no dummy load, there is no P story, there is nothing else. You just need to carry on with the original loading condition only. So here in the first segment, I have 10 Newton with me and X is the distance. So I would write down 0 minus 10x. Now this story ends over here because there is no other force in this segment due to external force, right? Now for a same segment, now listen carefully and try to understand. For a same segment, I will check that whether is there any possibility for the unit load, if that unit load exists in this segment or not. First of all, if it do exist, then you have to take moment. Otherwise, you can simply write down your moment equation as 0. So you can see here that in this segment B to C, this is point B. We don't have any unit load, unit moment, nothing in this B to C segment. So my equation small m becomes 0 for this particular segment, right? So here you need to now consider it carefully. And now our unit load method have already started from this stage, right? So you can see that there is no unit force, unit load in this segment. So I have written it general expression of moment as 0 for m, small m. Now let me go to the another segment. Here I will remove this just for ignoring the confusion. So here I have another segment that is called C to A. So here C is the origin, C to A is the segment, length is 0 to 2 meters given in the question. And now I will write moment equation due to external load in this segment. Now please understand, we have reached in the second segment, so whatever has happened with the first segment, that we will forget, and now my x starts traveling from here, but we have to consider external force at this level, right? So you have to take moment at this section, at a new section, at a x distance in second segment due to the first load. So this is very well known phenomenon to you. So 10 into this 3 meter will be by default and plus x. So the moment equation for this segment will be minus 10 into x plus 3. Okay. And now since I have unit load also, is there any other external load? No. So your capital M story ends over here. So you have to write it as it is. And now you can see that you have a unique load waiting for us to be utilized for this segment also at the x distance from point C, that is the origin, right? You can see here we have mentioned C over here as origin. So now this is unit load and distance, that is x, that is unknown distance. It will also create the clockwise moment over here for the second segment. So that is negative 1 into x, right? So friends, this both stories end over here. So as far as the development of moment equation for external loading and moment equation for unit loading, both we have separately developed for separate segments. Clear? So I'm sure that you all are very clear on how to develop this equation, or how we have developed this equation. Now, what is the let me compare this with the earlier methods where we used to do the same exercise, but with a different, let us say, treatment. Like we used to develop M, and then we used to take del M upon del P or del M upon del M again, right? Likewise, right? So that was the difference earlier that we have seen. But now here, it was necessary for us earlier that we had to have term P in our equation, if you recall, right? So here now that limitation has been removed. So that is why I would say that this is more flexible method than the earlier, because you don't need to have any P type of compulsory force and later on you declare it that either it is 0 or either it is having some value, nothing to do with that. So separately keep your forces together, I mean on the segments, particular segments, and apply them one by one, layer by layer. So here you can see that you have a segment called B2C segment. So this is, I would say, this is your B2C segment first, right? So that's what you have written here. You have also mentioned its length, that is 0 to 3 meter here, right? And further, you need to develop the generalized moment equation due to the external force first of all. So that is what exactly we have done. At the x distance, we have taken the moment for this segment, and for the unit load which we have applied at the interested point C. Now you can see that there is no unit load existing between B to C. So there is no scope for any moment equation due to unit load. This is the unit load value and this is the external load value, right? Let me clarify that. So here you can see that there is no mention for any unit load, so it has to be 0. And now we will go to the second segment. So that is C to A, where C is the origin here. CA is the segment's name. 0 to 2 meter is the length. You can read it here itself. Right. And now we have to again take the moment, generalized moment equation for this segment due to external load only, because in this segment you can see here, these are the column, this is a column in which you have to only write moment equation due to external load. If there is no load, then there won't be any equation, please understand. So since we have external load, and that load we need to consider for second segment now. So this load of 10 Newton has to cross over the distance of 3 meters before reaching it to the origin. Once it reaches to the origin, then it's again the forthcoming journey starts. So now you can take moment of this 10 Newton force at this location X, but you need to consider the earlier distance also before you reach to the X distance. So that is why we have mentioned X plus 3. Now this is again a routine practice for you, but the only difference is we are not mixing the things together. We are keeping external load differently, and we are also keeping unit load differently, and we are applying them one by one. So here now, once you have applied the external force, now its story is ends over here, and then you have to apply unit load. So now I will be applying unit load again at a x distance. So I will be getting my moment equation for unit load force also. So I hope that now we have got to know the difference between earlier practices and this practice, right? Earlier, according to the Castigliano's first theorem, we need to apply, if this would have been the Castigliano's first theorem, we need to apply P force over here, and that we need to include in your all the calculations. Later on, you can say that P is equal to 0, and then you can get your final answer for delta C. Now, instead of declaring anything which is a dummy load or false load, instead of that, what we can do is we can apply a unit force which has a unit value. Value of this force is 1 only. That's why it is called unit, right? So the name of this method has emerged from this fact that if you are interested in deflection, apply unit load. If you are interested in rotation, that is theta, then apply unit moment. Its value will be again 1 unit only, right? So here this value is 1, and here the moment value is also 1. So instead of point load, if you would have applied rotation, you would be getting theta. Right now we have applied point load, so we will be getting deflection. So now the only procedure which is remaining, that we have to use these terms in this format, right? So this format is very important for us, and everybody has to focus on that. I'm talking about this format of equation, right? So don't worry, I will be rewriting this. I just wanted to first of all you understand the difference between the Castigliano's principle 1 and this unit moment unit load method, right? So now let me copy this because I need some extra sheets, so I forgot to add them earlier. So now I'm adding them because I want clear board so that I can use it for the further calculations. Okay, and before we do it, let's duplicate this so that we can have some more slides to be utilized for the overall calculation. All right, so now in the continuation we are discussing this numerical, and let me go ahead with this and demonstrate again how to finally obtain the all the necessary values. So let me change the color here. It is to be black. It is black now, and okay, the thickness is fine. So friends, let's continue with the numerical. This is a third step, right? Once you have written the equation, overall equation for segments, now in third step, what we shall be doing is we shall be writing the equation for delta C. Now this is A, which is fixed. On this side, we have 10 Newton. Somewhere here we have point C. This is point B. This is 3 meters and this is 2 meters. Okay, now we will be putting up the standard relationship EI 0 to L equation, generalized equation of moment due to external load into small m, generalized equation of moment due to unit load into dx. It is as simple as that. So let's go ahead. 1 upon EI. Segment wise, we will write down. So first segment is 0 to 3 meters. Capital M is minus 10x. So I will be writing here minus 10x, right, into small m expression. You can see here that it is 0. So I will be I'll be writing 0 here. Dx, it completes the first segment, and plus I will be writing second segment. Don't worry, I'll be going across horizontally only. This is 0 to 2 meters because we are now in second segment. So let me write down the expression for m in this segment, that is minus 10 into x plus 3. So here I will be writing here minus 10 into x plus 3. That is my primary expression for capital M, and for small m it is minus 1. Here you can see, right, it is negative 1x. So I will be writing here it is minus 1x dx. Okay, so that's all my friends from this generation of the generalized expression and equation. Let's write down delta C. As you can see, this term will be nullified because it is 0. So 1 upon EI, right? Now we have only short expression that I will also be simplifying. 0 to 2 meters. This negative sign and this negative sign cancels each other. So that we will simply write down 10x plus 30, right, into x dx. So let me write down 1 upon EI, that is still 0 to 2 meters. And now I will multiply x, so 10x square plus 30x, okay, dx. Now we are ready to integrate it, and delta C is written as 1 upon EI as usual, 10x cube upon 3 plus 30 into x squared by 2. The limit of integration is 0 to 2, right? So I will be writing here 1 upon EI. Let's insert 2 meters value. So 10 into 2 raised to cube upon 3 plus 30 into 2 raised to square by 2. So this is how we get our final expression. I'll be writing here delta C equals to what? 1 upon EI. So this becomes 80 by 3 plus 120 upon 2, right? So now let's go for it and let's obtain the exact value. So it is now expressed as 1 upon EI, as this will be 80 by 3, so it gives you 26.67 plus 60, right? So total will be 86.67 upon EI. So now friends, we can understand that this deflection is always expressed in kilonewton into meter cube. So if I have the value of EI, so I'll be writing here into 12 divided by, let us say EI is around 6 into 10 raised to 13. Total EI value is 6 into 10 raised to 13. So I will be getting the answer of 1.4 mm out of this. So due to the 10 Newton force, this is the value of EI, numerical value. I had to give it earlier also, but it's okay. Newton into mm square, and that is what we have used here. So we got this answer with us. Now, instead, if I'm interested to find out theta c, then what should I do? Any idea? So if it is the required quantity, then I need to apply unit rotation over that. So let me demonstrate it quickly again so that you can have a complete idea how to do it, how to use it. Let's say this is, and the interesting part is you can do it in a line itself, in a same table. You can go for another quantity also. In that case, you just need to give another name. Let us say M1. So M1 as small m is unit load and small m1 is unit moment. That's it. We could have do it here also, but now let me quickly show you. This is load 10 Newton. Okay. This is what is 2-meter distance. This is point C, of course. This is point A. This is point B, right? This is 2 meter. This is 3 meter. And now we are interested to find out theta C, rotation at C. Right? So we'll develop the same table. However, B is the origin. Okay. We'll write down here. B to C is the segment. 0 to 3 is the length over here. Capital M is nothing but 10 into x, remains as it is, right? And now I will be writing small m. Now I have to apply unit moment here. Value is 1. Here there is no moment in segment B to C, so I will be writing 0 again. I have another segment with origin C, so C to A. 0 to 2 meter is the distance here. And now I will be using this minus 10x plus 3 meters, right? So that is my equation, that's all. And now I have 1, that is unit moment, and I'll be taking negative it again because it is clockwise. So I'll be writing minus 1, that's all. That's the only difference. So now same story repeats. Theta c, I will be avoiding first term. Directly I will be writing EI, second term only. 0 to 2 meters, minus minus becomes plus. So 10 into x plus 3 dx equals to 1 upon EI, 10x plus 30, right? Still it is in integration phase, so it is dx. Now please all of you understand this is theta c equals to, let's say 1 upon EI still, and let's say 10x. Now I'm integrating, so 10x square by 2 plus 30 into x. Length of integration is 0 to 2, so I'll be including all these values together, and it's very easy to do it. 2 into 2, 4, right? So 4 here, it is 2, and this is 60, right? So that's it. Now we can have 100 by 2, so it is 50. Sorry, this is 40, so divided by 2, so it is again 20, so it is 80 upon, let's say, EI. And we already know that it is always kilonewton into meter square. So here it will be 9. So 80 into 10 to the power 9 divided by 6 into 10 to the power 13. So you know the answer, that would be, let's say, 80 divided by 6. So it will be divided by, so it will be 1.3 into 10 to the power minus 4. It's very, very small quantity of radius, right? So that will be the final answer over here of theta c. So this is how we can use the unit load method to obtain the rotation as well as deflection of the beams, right? Of the any let us say determinate beams practically. So let me give you one more numerical which we can take it for the practice. And now I will be asking you to help me. So as usual, what we do in our regular practice, I will be asking to you to help me out for this expression, this numerical, sorry, this is our second numerical. So I have a UDL on a let 1, 2, 3, 4, 5, 6, 7, 8. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, so up to 8, that means 4 meter. Let's say I have 4 meter length, and in 2 meters of the length, I have almost half of this. I have a point load at the end. So let's say this is 50 Newton, and let's say this is 15 Newton, sorry, kilonewton. I need to change the units. 50 kilonewton, and here it is 15 kilonewton per running meter. This is 2 meter, of course, half of the earlier. Now the only difference is we need to take care that here we have 2I and here we have I. So in actual, if we draw the sketch of this numerical, it becomes like this, something like this. So it goes like something like this. So this would be the fixed end for that, and here you have point load, and here you have UDL like this. So that is 4 meter, and this is 2 meters. So that's a given condition for you, and here we need to calculate. Let's say this is A, this is again the point B, and now you have point C. So now I am interested in both the quantities at point C, delta C and theta C. What would be the answer that you need to obtain, right? So at least we can develop the initial steps. We may not be able to complete it fully because we have time constraints, but definitely you can do half of the majority of the work here, and then later on you can do it on your own. And let me give you the value of this is 6 into 10 raised to 13 Newton into mm square as EI, right? So I have already specified few things, that this is a tapered beam, or let us say non-uniformly varying beam size. So moment of inertia is double in this area A to C, and moment of inertia is constant for C to B, that is only I, and that will reflect in your equation also. And here I have mentioned the values of the UDL as well as point load. So now let's start trying to apply the unit load method for calculation of delta C first. So we are interested in vertical deflection. So let me show you the profile of the deflection of this beam. You can see here that let us assume that this is the axis of symmetry for this straight line, which is straight before application. You can see here that there will be slight reduction in the deflection here because you have 2I here and you have one I only. So it will deflect gently up to this point, and then it should deflect like this, right? So right now we are interested to find out this delta C. Okay. So for that, what we will be doing right now, since we want to find delta C as well as theta C at a same location, so what we'll be writing, we will be writing both the expressions together. How and what, let me demonstrate you first. So again, we'll divide popularly our segments B2C and C2A. So for B is the origin, right? B2C is the segment. Right. Now, what's the length? 0 to 2 meter. So the first expression for capital M, it is necessary to mention it. So due to the external load, M means capital M means external load. So in this segment, we have only one load which is externally applied, that is 50 kilonewton. So I will be writing negative 50 into X, okay, because of the X as a distance. Now, I will be applying unit load first of all. So I have to write down somewhere here as my reference that I have applied unit load for the first case, and on a same structure I will be applying unit rotation also, right? And what I'm going to symbolize, this external load we have symbolized with capital M. So point load will be symbolized with small m, and rotation or moment will be symbolized as M1. Okay, so let me write them the equation. Due to M, it is 0 because there is no point load in this segment. So I will keep it blank as it is. And there is no rotation also. So I will be keeping M1 as 0 as well. Right. So for this segment, the only expression that we have is this. Now we can go for another segment, that is C2A. So C is the origin, C2A, 0 to 4 meter is the length. Now due to M, so while you are writing the expression for common or generalized moment equation for segment C2A, do not forget the earlier externally applied force also. So as usual, we know this practice. So minus 50 x plus 2, okay, minus, now you are here somewhere. So this much UDL for the x length will be considered. You already have the value. So minus 15 x squared by 2. That is what is your expression for capital M only. Now let's go for unit load, right? So for unit load, it is 1, come here. Now 1 is there and unit load is there, and this is a distance. So it will be minus x, that's all. And for M1, when you are be clear that when you are using rotation, unit rotation, don't consider unit force, right? Because you can see we are writing in a separate columns. So here for that expression, you just need to write down minus 1, that's all. Now for deflection, it is needless to tell you that for deflection, we will have one expression, and for rotation, we have another expression. For deflection, we will be using capital M into small m, and for rotation, capital M into M1. That's it. So I hope you get the clarity how to use these expressions, this relation. Other terms are common like integration and dx and all this, and 1 upon EI like that. All are common again for both cases, right? The only difference is when you are interested in deflection, use small m expression, and when you are interested in rotation, use small m1 expression. That is dedicatedly meant for moment only, you can see here. Right, so likewise, now I think the job will be easier for you, and you try to complete this numerical in all respect, and try to find out the value of theta c for me, and theta c for me, delta and theta c, right? So you get the numerical answer of both this, and tomorrow I shall be giving you the answer to these questions, and then we'll go ahead of using this unit load method for some more numerical practices, and then we'll go for indeterminate structures, like how we can use unit load method for indeterminate structures. They will be providing us, first of all, the reaction values, and then we will be using them for further applications. See, unit load method is applicable to any type of structures: determinate, indeterminate, trusses, frames, half frames, whatever type of the structure you can think of it, you can apply unit load method for obtaining the variety of the values like rotations, deflections, reactions, and internal forces. So it is very versatile and very convenient also, as you must have observed in today's numerical sessions. Like you can see here that you just need to develop one general common equation where only unit load is applied, and it will give you deflection. If you apply unit rotation, it will give you the rotation at that particular point. Unit moment will give you unit rotation. Unit force will give you unit deflection. So this is how we have slowly begun with the utilization of unit load method in the structural analysis. So it is generally considered as a part of the energy principles. However, there is nothing to do with the energy concepts for this method. But usually, since it is similar to the Castigliano's energy principle number 1, it is very popular and it is commonly referred along with the virtual work also. So it's a unit load method or virtual load method. You can apply unit value of 1 or non-zero ideally. So that's why it is also sometimes referred as virtual work also. So it's a unit load method, you can virtual load method. And today we have seen that how to use it for simple numerical solution of the simple problems. And we have successfully completed one numerical also, and half numerical, another numerical to the formation of the equation. You try it on your own, don't worry, otherwise I will also help you to solve it. You just write down this question in your notes so that you can do it on your own, and do not forget this important variation, right? It is 2i here and it is I here. Where it will be reflected? It will be reflected in the denominator of the particular segment, right? So that you will get the right answer. So try it. And in case if you are unable to solve it, don't worry, I'm there. So tomorrow, first of all, we'll complete this numerical, and then only we'll go ahead for the further application of unit load method. So thank you all, and stay safe. And still pandemic is on, so take care of yourself, good care of yourself, and practice, practice, and practice. That's the only solution for avoiding the conditions of lengthy papers and all. So thank you for sharing your review and feedback regarding the mid-sem exam with me, and together we'll carry on with the further numerical exercise in tomorrow's session. So we'll meet tomorrow, and till then, keep practicing. Thank you all for joining this.